So in order to design synchronous counter, I like to start with this document that I have right here. If you're interested, let me know later and I'll share that with you. It's on my Google Drive. I'll send it to you later, okay? Let me know. But here, I think that the best way of showing how to design a synchronous counter using SSI and SSI only will be to go through an example, okay? So Grayson, would you please give me an example of a counter that can be done with 3 flip-flops? That means a counter that has numbers up to the number 8. Just make up a sequence of numbers up to the number 8. It really doesn't matter what it is. It can be anything.
So it could be anything from 0 to 8?
Yeah, 0 to 7.
7, yeah. Does it have to be up or down?
Matter, anything. That's the beauty of this. You can do anything you want.
Be like 1 to 4?
It could be 1 to 4, or it could also be what we did for the 60-second timer, the 0 to 5, if you want. We can do that.
Okay.
0 to 5?
Sure.
Okay. So we're going to essentially, the goal right here, and I'm going to write it down here. The goal will be to go 0, then 1, then 2, then 3, then 4, then 5, and after the 5 to go back to the 0. That's the goal, okay? And I'm going to do it with JK flip-flops. So on this table above, that's the key table right here to design those counters, okay? On the left, we're going to have 3 flip-flops, A, B, C. The flip-flop A is going to be my most significant flip-flop, using essentially producing the most significant bit. And the C will be my least significant flip-flop, producing the least significant bit, okay? Why? I just need to make a choice, and this is a choice I'm making now, okay? And because we have a truth table right here, essentially, I'm always going to have this combination right here of all the zeros and ones that you can get. Basically, it corresponds to the binary count, 0, 1, 2, 3, 4, 5, 6, 7, okay? And so that's the current count. This here, in those 3 columns with A next, B next, and C next, I'm going to have the next count, okay? So here is how it's going to work. If right now we have 0, 0, 0, that's this number right here at the bottom, right? It's the number 0. What is the number we should have next? 1, right? But 1 in binary will be 0, 0, 1. Correct? So if now I am at 1, I'm at 1 right here, what do I need next? Next, I need a 2. And 2, as you know, is going to be 0, 1, 0. If now I am at 2 right here, 0, 1, 0 is 2, the next number I need will be 0, 1, 1. I need a 3, which is 0, 1, 1 in binary. And so the next one will be the number 4. And so it's not the next one because of the one above, but it's because of the choices of a counter that we made. This would be 1, 0, 1, right? And if you look right here, this number right here is 1, 0, 1. What do we get after 1, 0, 1 in this counter?
Would it be 0?
Absolutely, it would be the 0. That means that right here, I'm going to have 0, 0, 0, because that's what we want for the count, right? And so what's going to happen to the last 2 rows right here? Well, this number right here, 1, 1, 0, in decimal is the number 6. But in our counter, this is never going to happen. So we don't care because this is not going to happen. So I can put don't cares like this. Okay? Now, how do we proceed? Well, you can see that I have 6 more columns right here in this table: JAKA, JBKB, and JCKC. And the reason for those columns is because we are dealing with JK flip-flops. And in order to control what's going to happen after the clock triggers, we need to control both J and K. Okay, so if we want to go from 0 to a 0 right here, what are the values of J and K? Well, it's actually why I put this table right here. If we want to go from having an output equal to 0 right now to having an output after the next clock signal also being equal to 0, then J and K have to be either 0 and don't care. J must be 0, and we don't really care what K is equal to. So this here allows me to write 0, don't care right here. The next row, I also go from 0 to 0, and the next one from 0 to 0 as well. So that will be 0, don't care, and 0, don't care as well right here. Okay. The fourth row down on the A column, though, we go from a 0 to a 1. To go from a 0 to a 1, I need to look right here, and that's going to give me 1, don't care, which tells me I'm going to have 1, don't care right here. The one below that, I'm going from a 1 to a 1. That's going to be don't care 0. How don't care 0? Well, right here. To go from a 1 to a 1, it's don't care 0. The next one will be 1 to 0. To go from a 1 to a 0, it's going to be don't care 1. The next one, to go from a 1 to a don't care and a 1 to a don't care, well, it's a don't care. So I'm going to have don't care everywhere right here. Okay. So this is what I did right here for flip-flop A. I need to repeat the process for flip-flop B. I'm going to change the color right here. So for B, I go from 0 to 0 right here. So from 0 to 0, it's going to be 0, don't care. So I'm going to put 0, don't care like this. Then we're going to go from 0 to 1. 0 to 1 is 1, don't care. Then we go from 1 to 1. 1 to 1 is don't care 0. Next, we go from 1 to 0. From 1 to 0 is don't care 1. So it's a little long, but it's very powerful. Next is 0 to 0. Next is 0 to 0. So to 0 from 0 to 0, it's 0, don't care. So you're going to have 0, don't care right here. And then it's going to be don't care, don't care. Okay. The last 2 rows are going to be don't cares like this. Okay. Let me change the color for the last one, for the flip-flop C. So what I like about C is that it's going to be toggle mode, right? Look, it goes from 0 to 1 right here. And to go from 0 to 1 is going to be 1, don't care. So it's going to be 1, don't care, 1, don't care, 1, don't care. Or it's going to go from 1 to 0, 1 to 0, 1 to 0. And from 1 to 0, it's going to be don't care 1, don't care 1, don't care 1, don't care 1. Okay. So we have all our values for JAKA, JBKB, JCKC, right? So now we need to go with K mapping. Okay, so I have prepared the 6 K maps right here. And so JA, we're going to have 0, 0, 1, 0, don't care, don't care, don't care, don't care. KA is going to be don't care, don't care, don't care, don't care, 0, 1, don't care, don't care. Okay. So I'm going to group this like this and group this like this. So based on this, that's going to give me JA equal BC and KA is equal to C. All right, done. Let's do the same thing with JB. JB would be 0, 1, don't care, and don't care, don't care, don't care, don't care. And KB will be don't care, 1, 0, and don't care, don't care, don't care, don't care. So let's highlight the groupings right here. Right here, we're going to have this as a nice grouping of 4. And here we're going to have a nice other grouping of 4 as well. 0, 1, don't care, don't care. Wait a second. JB, did I
Damn it,
make a
wouldn't
mistake?
our 5 and 6 be zeros?
Yes, I made a small mistake. That's what I always double check. Yep. So let me get rid of this right here because this one is not don't care, don't care. It would be 0, 0. Right? Is that what you were referring to?
Yeah, yeah.
So JB will be this one in that case, and KB will be this one. KB is good. All right. So that means that JB is going to be A naught C, yeah, and KB will be C. Right, beautiful. For JC, we're going to have one, don't care, one, don't care, one, and don't care, and one, don't care. And for KC, it's going to be don't care, one, don't care, one, don't care. Oh, look at that. They are a big, huge group of 8 right here. We can group all of this in a big group of 1, all of this in a big group of 1. And so that gives us JC equal VCC and KC equal VCC. Okay. So this is our design if we didn't make any mistakes. So how do we proceed with something like that? Well, it's actually quite simple. You would get your flip-flops. Okay. So that's going to be your JK flip-flop with your clock right here. That's going to be your Q. Okay. We need 3 of those. So I'm going to make 3 of those like this. Since it is a synchronous counter, I'm going to have my clock signal right here that goes to all my clocks at once. Okay. This on the left, it's going to be my most significant flip-flop. This is going to be my second flip-flop. This is going to be my least significant flip-flop. And if I now look at the logic that I have from above, JA has to be equal to B and C. So JA is going to be this one. So I'm going to have an AND gate right here that goes to JA, and that has to come from B and C. So B is going to be this one. B is going to be this one. And C has to be equal to this one. So I have B and C for JA. And KA is just C. All right, well, KA then is just going to be connected like this to C. Right? What about JB? JB is A naught and C. Okay, so JB, let me change the color from AND gate. I need an AND gate right here in front of JB. It's going to be A naught and C. All right. So A naught is going to be coming from Q naught right here. And C is going to come from the one above right here. That's still C. All right, wonderful. And KB is C. Oh, that's the same as this one. So KB is C right here. Wonderful. And for flip-flop C, we said that JC is equal to KC is equal to VCC. Okay, so I'm going to have a little VCC right here. And I'm going to connect those two right here to VCC. And then if I connect the output right here of the 3 flip-flops, so this one, and this one, to a decoder and then to a 7-segment display, I will have my counter and it's done properly like this. Okay. And something like this does work and does not have any ripple and works extremely well and reliably. Okay.